Okay, in this video we're going to look at problem 2.56 from our text. So here's the problem. We're looking at a thermodynamic cycle, and so we're going to start at the same state that we're ending, and the total energy for this thermodynamic cycle is going to equal 0. We start at state 1 with volume of 1 meter cubed and a pressure of 1 bar. We have a constant volume isochoric expansion to 3 bar, and we're given the change in internal energy for that process. In process 2, we have a constant pressure expansion to 2 meters cubed. And then going from step 3 back to 1, we have an adiabatic compression with work of negative 120 kilojoules. And the problem is asking us to determine the net work for the cycle. So work of the cycle. And the heat transfers for processes 1 to 2 and 2 to 3. And then to analyze and determine whether it's a power cycle or a refrigeration cycle. So first let's sketch out this process. We plot P versus V. We start at 1 bar to 3 bar, and we have 1 cubic meter to 2 cubic meters. And so at state 1, we are here at 1 bar and 1 cubic meter. Going from state 1 to state 2, we increase the pressure to 3 bars, and we have a change in internal energy for this process of 400 kilojoules. Going from state 2 to state 3, we have a constant pressure or isobaric expansion, so it's a horizontal line since the pressure is not changing, to a volume of 2 meters cubed. And then finally going from 3 to 1, we have an adiabatic compression. I'm going to make this a dashed line just to say, to denote that I don't exactly know that the pressure and volume are following this line. But because it's adiabatic, we know that the Q for this process is 0. We also know that the work is negative 1,120 kilojoules. And so this is our process. And again, because we have this entire thermodynamic process, we know that the change in energy over the entire thing is equal to 0. And so Q for the cycle equals work for the cycle. We also know that there's no changes in kinetic or gravitational potential energy, so for each process, the change in internal energy is equal to Q minus W. So let's go ahead and put this in table form. So we have these 3 different processes, 1 to 2, 2 to 3, and 3 back to 1. And for each of these processes, we can look at the change in potential energy, the heat transferred to or from the system, and the work done on or by the system. We'll go ahead and fill this with the information we know. We know that for the step 1, we were given that the change in internal energy is 400 kilojoules. We know that there was no increase in volume, and so there was no work done by the system. So work is 0 kilojoules. We also know for process 2, since we have an expansion at constant pressure, work is P delta V, which if we go ahead and solve that out is 300 kilojoules. So in that expansion, the system is doing 300 kilojoules of work. So that's all we know for process 2 to 3. For the final process, from state 3 back to state 1, we know that the work is negative 1,120 kilojoules. And because it's adiabatic, we know that Q is 0. And so this is what we know or can calculate from the problem so far. At this point, let's go ahead and remember our equations. So since the change in energy since it's a thermodynamic process, we know that the sum of all the delta U's is 0. Because there's no ultimate change in energy. We also know that for each process, all of the change in energy is the change in potential energy. And so for each step, delta U is equal to Q minus W. And finally, at the end, for this entire cycle, the Q of the cycle is going to equal the work of the cycle. Should I write that down here? And so knowing those three pieces of information, we can go ahead and fill in the rest of this table. Okay, so for this first process, the change in U is 400 kilojoules and no work was done. Therefore, the heat transfer also has to be 400 kilojoules. For we know here that the entire work done over the entire cycle is negative 820 kilojoules. So 820 kilojoules of work is done on the cycle, and therefore the entire heat needs to be negative 820 kilojoules transferred to the system, which means if the heat for step process 1 to 2 is 400 kilojoules, then the heat transfer for process 2 to 3 has to be negative 1,220 kilojoules. Delta U at every step is Q minus W. So delta U here is negative 1,520 kilojoules. And for this final step, delta U is Q minus W, and so delta U needs to be 0 minus negative 1,120, so delta U is 1,120 kilojoules. And we can see that the sum of all of these potential energies is in fact 0. So there, we found the change potential internal energy, the heat transfer, and the work for every step. Finally, the problem asks us to determine whether it's a power cycle or a refrigeration cycle. Well, we saw for this problem that the Q of the cycle equaled the work of the cycle, which is negative 820 kilojoules. And so in this cycle, we have a negative Q, so heat is being transferred from the system, and work is being done to the system. And so where we have a situation where we are doing work on the system in order to get heat from the system, this needs to be a heat pump or refrigeration cycle.